Welcome to the deep dive. Have you ever found yourself, really struggling with a complex web search?
Oh, definitely.
That feeling, right? Wrestling with some tricky question, and suddenly you've got, like, a dozen tabs open.
Yeah, trying to piece it all together.
Yeah, checking sources, figuring out what's what, assembling an answer. It's just a huge amount of manual effort, isn't it?
It really is.
For decades, web search has basically been user-driven. It gives us information, sure, but we have to interpret it, assemble it.
Puts a lot of cognitive load on us.
Exactly. Especially now, the digital world's just getting more complex, the questions are harder.
Yeah, it keeps growing.
But what if AI could actually, take on that heavy lifting for you?
Like a research assistant.
Sort of, yeah. Imagine an AI system acting like this, tireless, super efficient researcher.
Okay, I'm listening.
So today, we're taking a deep dive into this really fascinating, fast-moving area called Agentic Search systems.
Agentic Search.
Right. Think of them as sophisticated AI agents. They can autonomously navigate the web, interact with websites.
Click buttons, fill forms, that kind of thing.
Exactly. And synthesize information from multiple sources, then deliver these comprehensive answers all backed up with citations.
So, not just a list of links anymore.
Not at all. It's a huge shift in how we get information online. It promises, more efficiency and less mental strain for us.
That sounds pretty good.
But here's where it gets really interesting. If these systems are so advanced, doing all this complex stuff, how on earth do we even evaluate them properly, like reliably?
Yeah, that's the tricky part.
How do you measure an AI that might spend an hour, take hundreds of actions across, say, dozens of websites just for one complex real-time question?
The old methods probably wouldn't work.
Exactly. Traditional, static ways, they just don't cut it.
Right.
So our mission today is to unpack this groundbreaking new research paper. It really tackles this evaluation crisis head-on.
Okay, what's it called?
It's titled Mind 2 Web 2, Evaluating Agentic Search with Agent as a Judge. Comes from a team at The Ohio State University and Amazon AGI.
OSU and Amazon AGI. Nice.
And they didn't just point out the problem, they actually built, an innovative, comprehensive solution.
So they've got a new benchmark and a way to evaluate.
Precisely. We're going to explore exactly how they built this new benchmark, dig into their novel Agent as a Judge evaluation method.
Agent as a judge. Sounds intriguing.
And maybe most importantly, reveal what they found when they tested these cutting-edge AI systems against actual human performance.
The AI versus human comparison. Always interesting.
Get ready for some genuinely surprising insights into the future of information gathering and really what it means for you, the learner.
Okay, let's get into it.
All right, let's start by really unpacking the evolution of web search. For so many years, that basic interaction, it hasn't really changed much, has it?
No, not fundamentally. You type keywords, get links.
Right. We type a query, get a ranked list of URLs, and then, it's all on us.
Open, read, synthesize, repeat.
Exactly. Manually open the links, read through everything, piece together information from maybe multiple pages just to answer one slightly complex question.
That's been the standard workflow.
Yeah, even while the tech behind it got way more advanced, We saw TF-IDF early on.
Yeah, term frequency, document importance.
Then PageRank. Analyzing links.
Ranking based on authority.
And now sophisticated machine learning for ranking. But through all that, the interpreting, verifying, assembling, still us.
Always landed on the user's shoulders, yeah.
That's it, exactly. What's truly fascinating is that inherent user-driven nature of traditional search.
It retrieves, but you interpret.
Right. It finds the pieces, but you are the one responsible for making sense of them, putting them together into a coherent answer.
Which, as you said, puts a significant cognitive load on users.
And it just gets worse as the web gets bigger and our questions get more, complex and open-ended.
Definitely. But now, these recent, really revolutionary advances in large language models, LLMs, they've sparked a fundamental shift.
A paradigm shift, the paper calls it.
Exactly. We're moving way beyond just returning lists of links.
So what can these new agentic systems do?
Well, these new agentic search systems, powered by advanced LLMs, they have this remarkable capability. They can actually decompose a complex query.
Break down.
Yeah, break it down into smaller, more manageable subtasks. Then they can plan a multi-step approach to tackle them.
So they strategize.
Right. And crucially, they can iteratively search the web, actively interact with dynamic websites.
Like a person would. Clicking, scrolling.
Exactly. Clicking buttons, scrolling, filling out forms, all that. And then Once they've gathered all that scattered info, they synthesize it
into one answer.
into a comprehensive citation-backed response. So it's not just finding documents, it's like conducting research and providing an actual answer. The field itself has progressed incredibly fast. You can see a clear evolution.
How so?
Well, the early systems, just a few years ago really, were mostly what we'd call search-augmented LLMs.
Like early ChatGPT or Perplexity Search.
Exactly. They basically tacked search APIs onto the LLMs to get more up-to-date info than their training data had.
But they couldn't really browse?
Right, they were somewhat limited there. Interacting dynamically was harder.
Okay, what came next?
More recently, we've seen these LLM-based autonomous web agents emerge. OpenAI's Operator is an example.
Right, I've heard that.
These are specifically designed to browse the real-time web, much more like humans do. They often use visual perception.
So they can see the page layout.
Yeah, understand graphical interfaces, navigate more organically, apply filters, fill forms, generally act like a user. That was a huge leap.
Okay, so browsing like humans. And now?
And now the real frontier seems to be these deep research systems.
Deep research. Sounds serious.
They are. They're specifically optimized for, well, long horizon browsing and deep, extensive search behavior.
Meaning they can keep going for a long time on complex tasks.
Exactly. They use a whole suite of advanced tools, search APIs, sophisticated web browsing to conduct prolonged, detailed research on really complex topics. They're built for sustained effort, way beyond a quick lookup.
The tireless digital researchers we always wanted.
Kind of. Yeah, that's the goal.
So what's the big promise here?
The promise is, well, immense. By offloading many of those low-level, often tedious tasks.
Like breaking down the query, finding the right search terms, wading through pages.
Yeah, exactly. Even basic data analysis sometimes. Offloading that to a tireless AI agent. Agentic Search fundamentally promises to empower us, the users.
So improve efficiency and the quality of the answers.
Right. The main goal is to dramatically improve both search efficiency and the quality of information we get, which ultimately lets us focus our limited brain power on higher-level stuff.
Like making the actual decisions or critical oversight.
Precisely. Shift our attention from the grunt work of finding info to the crucial decisions, the critical oversight, the deeper analysis that still needs that unique human judgment and creativity.
Augmenting human intellect by automating the legwork.
That's a great way to put it.
That is a powerful vision. But like you said earlier, if these agents are doing all this complex, iterative work, maybe over hours, how do we actually know if they're doing a good job? How do you evaluate the output of something that complex? You know, an answer produced after maybe an hour, hundreds of actions, dozens of websites.
Yeah, it's not like checking a simple fact anymore.
The sheer complexity, the potential length of the answers, it just screams for a whole new way to evaluate. It sounds almost as hard as building the agents themselves.
That's absolutely right.
Yep.
And it raises a crucial question, critical for both, advancing the tech and for trusting it.
Just readiness.
Exactly. Automated, reliable evaluation. It's paramount for iteratively developing any AI, especially in these early stages.
And for agentic search specifically.
It's foundational for establishing trustworthiness.
Right.
Unlike old search, where you read the documents to check things yourself.
Right, you do the verification.
An agent that synthesizes answers. You have to be able to rely on it being correct and unbiased.
So automated evaluation is like the first line of defense against hallucinations.
Exactly. Against those plausible sounding but completely made up answers. Without really robust evaluation, we just can't fully trust these systems for important tasks.
So what's wrong with the existing benchmarks? Why don't they work?
Well, their limitations become pretty clear pretty quickly when you think about these complex agentic tasks.
Okay.
A lot of the current benchmarks for autonomous web agents, they mainly focus on tasks with, let's say, a moderate horizon.
Like not too many steps.
Yeah, maybe up to about 10 actions. And critically, tasks that can usually be done on just a single website.
Okay, so good for testing the browsing part? Like, can it click the right button?
Exactly. Useful for evaluating the browsing aspect, sure. But totally insufficient for evaluating the whole system when it's doing deep, multi-source research across the web.
What about benchmarks that do cross-website tasks, like OpenAI's BrowseComp?
Even those often make a big compromise to make evaluation easier. They tend to focus on tasks with predefined, static answers, time-invariant answers.
Often just a single string, you said.
Often, yeah, just a single string. And while that approach neatly sidesteps the huge challenge of evaluating complex, maybe even time-varying answers.
But it's not realistic.
That's what the paper argues, convincingly, I think. It systematically deviates from the true user query distribution. Are real questions. They rarely have one single, static, easy-to-check answer. They're dynamic, they evolve, they need synthesis.
Can you give an example? The paper had one, right?
Yeah, a great one from their figure 1. Imagine a realistic everyday task, something like, my budget is $200, $600. I need a bed frame, a desk, a chair, a floor lamp, and a 2-door wardrobe from IKEA. Oh, and make sure everything is white.
Okay, sounds like a typical shopping task.
Right. But there's no predefined static answer string for that. It absolutely requires interacting with live websites.
IKEA.com in this case.
To get real-time information. Prices change, availability changes, maybe even the specific white finish changes.
True. Things go out of stock.
Exactly.
Yeah.
So an agent trying to do this might take dozens, maybe hundreds of actions, just on the IKEA site alone. Navigating categories, applying filters, checking product details, maybe adding things to a virtual part to see the real-time total.
And that's just one website.
Precisely. More complex tasks could span many different sites, so it's clear. We desperately need new, much more sophisticated ways to evaluate these long-horizon, time-varying tasks that demand genuine deep search.
That example really hits home. Okay, so in response to these, well, profound challenges in evaluation, the researchers proposed Mind2Web 2. What exactly is this new benchmark? And how did they manage to build something so, well, robust and comprehensive to tackle such a tricky, dynamic problem? Sounds like a massive project.
It truly is. To put it in perspective, Mind2Web 2 is this novel benchmark, meticulously designed to rigorously evaluate agentic search systems on precisely these kinds of realistic long-horizon tasks.
Focused on real-time web search and browsing.
Exactly. Its core purpose is testing agents on that, mirroring the true complexity of how we humans actually seek information. This isn't about simulating the web. It's interacting with the live internet.
Wow, okay. What's the scale like?
Well, in terms of scale and scope, it's a really significant contribution. It consists of 130 high-quality tasks.
130 tasks, okay.
All carefully selected across diverse practical domains. And the construction. It involved over 1,000 hours of dedicated human labor.
1,000 hours just to build the benchmark.
Yes, a massive investment of time and expertise. Every single task went through multiple, painstaking stages of expert polishing and validation.
Why so much effort?
Well, this meticulous process was essential, not just for realism and complexity, but crucially for verifiability, making sure the answers could actually be reliably assessed both by humans and eventually by AI judges.
Got it. So what makes these tasks different? What are their key characteristics?
They focused on 4 key things that really set Mind2Web 2 apart. First, they have to be realistic and diverse.
Reflecting actual user needs.
Exactly. Authentic, practical needs across a wide range of domains. Things that provide real value if an agent solves them. Second, they're long horizon and laborious.
So definitely not quick lookups.
Right. They demand sustained effort, extensive web search, deep exploration, sophisticated information synthesis. They deliberately avoided short, quick tasks to really push the agent's limits.
Makes sense. What else?
Third, each task is designed to be objective and verifiable. This is critical.
Meaning clear evaluation criteria.
Yes. Criteria that can be concretely verified by checking the answer text and cross-referencing the cited source web pages. That objective verifiability is key for reliable, automated evaluation.
Okay.
And the fourth, finally, they actively encourage tasks that are time-varying.
Like the IKEA example, prices change.
Exactly. While it's not a strict requirement for every single task, many tasks involve information that could, and often does, change over time. Real-time prices, stock levels, current events. That's a critical aspect of real web interaction many benchmarks miss.
Okay. Realistic, long, verifiable, and time-varying. How do they actually collect these tasks? You mentioned a pipeline.
Yes, a very meticulous task collection pipeline. It's a testament to the rigor here. It involved 3 distinct groups of experienced annotators, computer science students, or professionals.
3 groups. Okay.
It started with task proposers. They generated initial ideas based on their own real search needs or specific domain guidelines. They did initial checks for realism, clarity.
So grounded in real problems.
Right. Then came the refinement experts. These were trained experts who worked closely with the proposers. They iteratively revised or filtered tasks.
Now, what was their main job?
To enforce strong alignment with those benchmark principles, making sure tasks were truly long horizon, unambiguously verifiable, robust, honing the raw ideas.
Got it. And the final stage?
Finally, validation experts. highly experienced folks, and critically, at least 2 independent validation experts manually attempted and verified each refined task.
2 independent experts tried to do the task themselves.
Yes. They rigorously focused on feasibility. Could a human actually do this? They looked for subtle issues, checked the practicalities of evaluation. Only tasks validated independently by at least 2 experts made the final cut.
Wow, that's a high bar, multi-stage human validation.
Exactly. It ensured incredible quality, complexity, and real-world applicability.
Did they measure how hard these tasks are for humans?
They did. To quantify the effort, they ran a human performance study on a random subset of 30 tasks. They called it subset 30.
What did they find?
The numbers are pretty revealing. The average time humans spent per task, 18 minutes.
18 minutes on average, that's significant.
It is. And some individual tasks took up to 44 minutes.
Almost an hour for one task.
Yeah. And on average, participants visited 8 different websites. But for one complex task, a human might visit as many as 31 distinct websites.
31 websites.
And within those sites, the average number of web pages visited was 110.
Wow.
With one particularly deep task needing navigation through 375 web pages.
That's a lot of clicking.
It is. And remember, these numbers are likely underestimated.
Why underestimated?
Because human participants had time limits. They could stop if they got stuck after 30 minutes, or if it took over an hour. Plus, humans make mistakes, right? They might miss steps due to fatigue.
True.
So it really highlights just how tedious and cognitively demanding these deep research tasks are, which is exactly what Agentic Search aims to help with offloading that legwork.
Makes sense. What about the types of tasks? Are they diverse?
Very diverse. The benchmark covers 6 broad domains and 24 subdomains. So agents are tested across a really representative spectrum of real-world needs.
Like what?
Well, for instance, a big chunk is lifestyle and leisure, 26%. Entertainment is 22%. Science and research is 18%. It shows real breadth.
Okay, building this benchmark sounds incredibly impressive, really meticulous. But, like we said, that's only half the battle. Once the agents generate these long, complex, cited answers, which can vary a lot, how do you automatically and reliably evaluate them? Check correctness, check attribution. That seems like another massive challenge, maybe even harder.
You're absolutely right. That's exactly where their novel agent as a judge framework comes in. And it's really the core methodological innovation here.
Agent as a judge. Okay.
The sheer complexity and length of these answers, hundreds, even thousands of words, it's just way beyond what conventional LLM as a judge methods can handle.
You can't just feed it all to a generic LLM and ask, is this good?
Exactly. You wouldn't get a nuanced, accurate judgment across all the specific criteria.
So what's their key insight? How does agent as a judge work?
The core idea lies in something they call generation verification asymmetry.
Generation verification asymmetry. Okay. What does that mean?
Basically, while the generated answers can vary wildly different agents, different search times, the evaluators, and therefore the judge agents, know in advance what each specific task is looking for.
Because the task definition is fixed.
Precisely. This lets them design a very specific task-by-task rubric that defines the evaluation logic exactly. It's not a general assessment. It's targeted, detailed verification, tailored to each unique problem.
Okay. And what does the rubric check?
It focuses on 2 main critical aspects. First, correctness. Does the answer fully satisfy all the requirements of the task? Factual accuracy, completeness.
Makes sense.
And second, attribution. Can every single statement, every claim in the answer, be verifiably attributed back to the cited sources?
Crucial for trust and fighting hallucination?
Absolutely. Ensuring the agent's claims are actually grounded in the provided evidence.
How is this rubric structured? You mentioned it's like a tree.
Exactly. Operationally, it's a hierarchical tree. Imagine the main task goal at the top, branching down into more granular criteria.
Down to the leaves.
Right. The leaf nodes at the very bottom represent the most specific criteria, and these always map to a simple binary judgment. 0 if not met, 1 if met.
Like, is the wardrobe white, 0 or 1?
Perfect example. Or, is the price information correct for this item? 0 or 1.
Okay, so binary leaves. What about higher up the tree?
The internal nodes aggregate these binary results from below, propagating them upwards towards the root, following different logical rules set by the rubric.
What kind of rules?
Well, the rubric can define critical nodes. These represent essential criteria. If a critical node fails, the parent node, and maybe the whole task, fails immediately.
Like the budget constraint in the IKEA example, if you go over budget, the whole list fails.
Exactly. Regardless of whether individual items were right. Conversely, there are non-critical nodes. These allow for partial scoring.
So if you needed 5 items and only got 4 right, you still get some credit.
Right. It allows for more nuanced evaluation than just pass-fail.
Any other types of nodes?
They also have sequential nodes. These reflect logical dependencies. So if a task needs you to find a paper, and then find the author's email from that paper.
If you don't find the right paper first,
then the check for the email gets short-circuited. No point evaluating the email if the paper itself is wrong.
Logical. How does the final score get calculated?
The aggregation logic uses a gate-then-average strategy. Critical nodes act as gates, ensuring essential constraints are met before any partial scoring from non-critical nodes is averaged in. It's quite sophisticated.
It sounds incredibly detailed. How complex are these rubrics?
Astonishingly complex.
Yeah.
Given how intricate the tasks are, the rubric trees themselves are highly complex. On average, 50 total nodes per rubric.
50 nodes on average?
Yep, with a maximum of an incredible 603 nodes for one single task.
Wow. And how deep do these trees go?
Up to 6 layers deep. It just shows the granular level of evaluation these judge agents are doing.
Yeah.
It's far, far beyond a simple keyword check.
Okay, so you have these complex rubrics. How does the judge agent actually use them? What does it do?
Right, so for each task, there's a dedicated judge agent. It's essentially an agentic workflow implemented as a Python script.
A Python script for each task's evaluation.
Exactly. These judge agents take the generated answer text, including the source citations, as input. They then systematically work through the rubric, evaluating each fine-grained criterion from the leaves up, and calculate the final score.
How do they do the actual checking? Do they use LLMs?
Yes, they primarily leverage 2 LLM-based tools. First, an extractor. It parses the answer text to pull out structured info item names, prices, URLs, things like that.
Okay, it pulls out the key facts.
And second, a verifier. This applies the actual verification. It examines the extracted text and screenshots of the corresponding cited web pages to determine if a specific statement is true or false.
Screenshots too, so it can check visual info.
Potentially, yes, or just verify the text against the actual rendered page content. The LLM used for both these tools is OpenAI's O4 Mini.
Why that model?
It's known for being highly capable, fast, and accurate at parsing and understanding tasks like this.
Okay, but writing hundreds of these complex Python judge scripts manually, that sounds impossible.
Prohibitively demanding, yeah. And this is where their ingenuity really shines.
How did they automate it?
They developed this clever LLM-based agentic code generation pipeline using a powerful model like Claude 3.7 Sonnet.
Known for good reasoning and long context.
Exactly. This pipeline automatically generates initial versions of the judge agent scripts based on the task description and rubric structure.
So the AI writes the code to judge other AIs?
Essentially, yes. And these generated scripts then go through iterative autonomous refinements.
What does that involve?
Things like self-debug, where the script gets feedback like error messages and tries to fix itself, and self-reflection, where it uses checklists to autocorrect common errors.
That's pretty meta, AI improving its own evaluation tools.
It really is.
How reliable is this whole agent as a judge system? Did they test it?
Absolutely crucial question. They put it through rigorous testing, extensive validation, 2-stage human refinement, and a subsequent human evaluation of the judge agents showed an exceptional 99% correctness rate.
99% correct. That's impressive.
But here's the truly fascinating, almost surprising part. Out of 720 verifications they checked, there were 35 discrepancies between the human evaluators and the automated judge agents.
Okay, so the judge agent wasn't perfect.
Well, get this. 27 out of those 35 discrepancies were actually due to human evaluator errors.
Wait, the humans made the mistakes more often than the AI judge.
In those discrepancy cases, yes. Think about that. It highlights just how incredibly complex it is to accurately evaluate claims in these long, multi-source answers, even for trained humans.
Wow.
And it strongly reaffirms the reliability of the automated judge agents, especially compared to other automated evaluation methods for simpler web tasks, which often struggle to get above 90% correctness. This system is designed to be more precise and tireless than even human experts for these specific detailed, long tasks.
That's a stunning insight, truly. Okay, so with this incredibly robust Mind-to-Web 2 benchmark and the super reliable agent as a judge evaluation, the researchers finally put 10 frontier agentic search systems through this gauntlet, tested them alongside humans on these really tough, realistic tasks.
The ultimate test.
So what did they actually find out? What are the current capabilities, the limitations of AI agentic search when pushed this hard? What surprised them and what surprised you?
Yeah, the results, which are laid out nicely in the paper's Table 3, they paint a really fascinating, nuanced picture.
Okay.
It really underscores that while most tasks in Mind-to-Web 2 are conceptually pretty straightforward, they don't require inventing cold fusion or anything.
Right, they're practical tasks.
Exactly. But their inherently tedious nature poses huge challenges.
Yeah.
Not just for the AI systems, but for the human participants, too.
How did that show up in the results?
Well, in the overall performance, both agents and humans had relatively low success rates. The best agents hit around 28% success, and humans were at 54%.
So even humans only succeeded about half the time.
On average for these tough tasks, yeah. It really drives home how demanding and laborious these tedious tasks truly are. They require immense attention to detail, sustained effort.
What else stood out about the agent performance?
Another key finding was this significant gap between partial completion scores and the success rates for the agents.
Meaning they could start okay but didn't finish perfectly.
Exactly. It indicates that current systems often show, let's say, initial competence. They can get a good chunk of the task right, they understand the goal, but they frequently struggle to fully complete tasks accurately, hitting all the nuanced details or comprehensive requirements.
It's like they ran out of steam.
Kind of, yeah. Or they miss critical details towards the end.
How did different types of agents compare?
Well, the weakest performers, maybe unsurprisingly, were ChatGPT Search and Perplexity Pro Search.
The search-augmented LLMs.
Right. Their main limitation was their restricted search horizon and relatively shallow information synthesis abilities. They're good for a quick lookup, but just not built for that deep, iterative research across many sources.
Okay. Who did better?
Most of the deep research systems achieved superior performance. That includes systems like OpenAI Deep Research, Grok Deep Search, Gemini Deep Research.
The ones designed for this kind of work.
Exactly. They're explicitly designed, trained, or prompted for extensive information gathering, sophisticated synthesis. That lets them engage in sustained, detailed work over longer periods.
Did they have extra tools?
Many do. They often integrate advanced capabilities like robust web browsing, actually clicking, scrolling, interacting dynamically, and even coding tools like Python interpreters to process web content more effectively.
What about OpenAI Operator? That's a web agent, right? How did it do?
Interestingly, Operator, despite being a highly advanced web agent focused on navigation, showed notably lower performance compared to those deep research systems.
Huh. Why would that be?
The paper suggests it's because web agents like Operator navigate much more complex, noisier environments. They manage huge action spaces, all the possible clicks and interactions on a page, and handle much longer, more intricate contexts.
So it's harder to plan and remember.
Exactly.
Yeah.
These factors pose big challenges for robust long-term reasoning, planning, memory management. Plus, deep research agents often use parallelized retrieval grabbing info from multiple sources at once, which gives them an edge over a sequential browser interaction in finding information quickly.
Did the deep research systems behave similarly?
Not entirely.
Oh.
They observed different behaviors in output style and length. Some, like OpenAI's and Hugging Face's systems, tended to produce relatively concise, precise answers.
Okay, to the point.
Others, like Gemini and Grok, consistently generated much longer responses, often thousands of words organized into structured sections. Intro, findings, conclusion.
More like a report. Did longer mean better?
That's the crucial insight.
Yeah.
No, despite seeming more comprehensive, increased length did not necessarily lead to better task completion.
Really?
Yeah. In fact, the paper notes that excessively lengthy reports can even be cognitively burdensome and suboptimal for users just trying to get a specific answer.
So more isn't always better. Quality and conciseness matter.
Exactly. It challenges that assumption.
What about giving the agents more time? Did that help?
Yes. They looked at test time scaling, figure 3 in the paper. They saw clear performance boosts as inference time increased.
Makes sense for complex tasks.
Right. It intuitively aligns with the task complexity. More time allows for more thorough retrieval, processing, integration, and doing multiple independent trials per task.
What they called pass at 3, trying 3 times.
Yeah. That substantially increased the likelihood of success, too. Suggests that even with some randomness, more attempts help nail down the answer.
What about those time-varying tasks? The IKEA example again. How did systems handle those?
Ah, that was very telling. Figure 4 shows it vividly. Most evaluated systems performed worse on the 57 tasks identified as explicitly time-varying.
The ones with real-time prices, dates, etc.
Exactly. This strongly supports the hypothesis that systems with no or limited live browsing struggle. They often give outdated or just plain hallucinated information.
But who did well on those?
Crucially, OpenAI operator and the human participants, both capable of interacting with live websites, achieved relatively on par or even better performance on these time-varying tasks.
So live browsing capability is vital for real-world accuracy.
Absolutely vital. You can't just rely on cached or old information for dynamic queries.
Okay, so there are limitations. But what about the overall promise? Did the results show potential?
Definitely. Despite the current limits, the evaluation clearly showed compelling early promise. The best system, OpenAI Deep Research, achieved an impressive 50–70% of human performance.
It's all taking less time.
While spending less than half the time human would. That's a significant efficiency gain.
Wow. Anything else surprising?
Yes, and this is profound. AI agents can sometimes even outperform humans.
Outperform humans? How?
Especially on tasks requiring great attention to detail and exhaustiveness. Humans, we get tired. Cognitive fatigue, limited working memory.
We make mistakes on tedious stuff.
Exactly. They gave an example. A task with really nuanced constraints in retrieving news articles. All the human participants messed up, oversight, carelessness, failures. The agents, they accurately interpreted the task.
Because they don't get tired or overlook details.
Precisely. Their tireless nature really emphasizes the potential for agentic search to augment our cognition by handling that detailed legwork prone to human error.
That's a powerful revelation. Okay, so we see the performance numbers, the time saved, even outperforming humans sometimes. But to really improve these systems, we need to know why they fail, right? The paper did a detailed error analysis, didn't it? Categorizing the shortcomings of both AI and humans.
Yes, exactly.
So beyond just the scores, what were the main reasons these systems fell short, and what does that tell us about where development needs to focus?
Precisely. Understanding these failure modes is crucial. They categorized errors along two main lines: correctness and attribution, then broke them down further, as shown in figure F.1.
Okay, let's start with correctness errors. What falls under that?
One common type was incompleteness. The answer just failed to fully meet the task needs.
How so?
Two subtypes here. Information not found, where the agent basically says, I couldn't find it, like a digital shrug.
Gives up.
Right. Then there was partial missing, where the agent gives fewer items or steps than required. This could be, as they put it, a degree of laziness, or maybe insufficient capability for really long tasks, or even system errors.
System errors?
Yeah, like with Hugging Face Open Deep Research. It often had errors invoking its search tools properly, leading it to just stop prematurely.
Okay, so incompleteness. What else?
Another big correctness error: criteria violation. This is where the answer explicitly contradicts cast criteria or makes factually wrong statements based on the text it found.
Like the budget example, listing items way over budget.
Perfect example. Listing a total of $1,277.97 when the budget was $600. And here's the fascinating bit.
What's that?
This was the most common error type for humans in the study.
Humans violated criteria the most. Why?
Often due to carelessness or misinterpreting details. Like that human annotator who listed University of Waterloo as being in the U.S. Simple mistakes under load.
But the AI did better here.
Yes. Deep research systems like OpenAI Deep Research actually surpassed humans in avoiding these. Because they are designed for exhaustive searches and sticking to requirements, their tireless nature pays off.
Interesting. Okay, what about attribution errors? Those relate to hallucination.
Often directly, yes. First type, invalid attribution.
What does that mean? Bad links.
Exactly. URLs provided are expired, wrongly formatted, or, most worryingly, just fabricated. Made up.
An agent just makes up a link.
It happened. They mentioned Hugging Face Open Deep Research fabricating an Amazon link without ever visiting Amazon. Even Operator, which does browse, sometimes reported incorrect URLs in the final answer despite visiting the right pages.
So trouble grounding the output correctly.
Seems like it, especially in long, complex interactions. Next, missing attribution.
Claims with no source cited.
Yep, just statements made without any backing link.
Yeah.
Web agents often aren't really trained for citation. And LLMs, with their huge parametric memory.
The stuff they memorize during training.
Right. They sometimes just produce information directly, hallucinate it, without doing a real-time search, even if the task needed one. It sounds right to the model, but it's not from a live source.
Okay. Any other attribution errors?
Yes. Unsupported answer. This is tricky. It means the information in the answer differs from the cited source, even if the link itself is valid.
How can that happen?
Two ways. A synthesis error. The agent incorrectly synthesizes info from correct web pages. Maybe it distorts a price from 220 to 230. This was more common in the search-augmented LLMs like ChatGPT search, which struggle with lots of sources. Humans sometimes do this too when overwhelmed.
Okay, synthesis error. And the other?
A retrieval error. The cited source is just totally irrelevant to the task. The agent might find a page that seems similar but isn't quite right, and then hallucinate details based on that wrong source.
Got it. So overall, how bad was hallucination?
A significant finding was just how pervasive hallucination was, defined as having either invalid attribution or unsupported answer. Even the best system, OpenAI Deep Research, had a 23% hallucination rate.
Nearly 1 in 4 answers had some hallucination.
Yes, and other systems were at 50% or more. And that's likely an underestimate, because hallucination can subtly cause other errors too. It's a major persistent challenge.
What about the human errors again? Just carelessness?
Pretty much. Humans didn't have incompleteness or hallucinate URLs, obviously. But they consistently struggled with the tedious nature of the tasks, leading to those criteria violations, misspellings, overlooking nuances, misreading things.
Which really highlights the potential for AI augmentation again.
Exactly. Handling the detailed legwork that trips us up due to fatigue or simple oversight. We're good at the big picture, less perfect at flawless execution of repetitive detail over time.
Any specific issues with the open source agents?
Yes. They noted Hugging Face Open Deep Research, the only open source one tested, often showed information not found errors due to problems using its tools correctly or mistakes in its generated code. It just stopped too soon.
Suggesting what?
It suggests that just using off-the-shelf LLMs might not be enough for robust deep research systems. You probably need significant fine-tuning or specific tailoring for these demanding long-horizon tasks.
Yeah.
More engineering is needed than just plugging in a big model.
Right. This Mind2 Web2 benchmark is clearly a huge step forward, a powerful tool for pushing AI agentic search. But like any research, it has limitations, right? And broader implications.
Absolutely.
What did the researchers acknowledge? And what should we, keep in mind as this tech advances? What about the bigger picture ethically?
That's crucial. And the researchers are commendably transparent about several limitations. For instance, task coverage and scope.
130 tasks can't cover everything.
Exactly. While diverse, they can't encompass all real-world scenarios. They explicitly excluded vague or highly subjective queries to ensure verifiability. Practical, but it means the benchmark doesn't cover every type of human question.
Okay. What else?
Evaluation framework assumptions. Their framework relies on URL-based attribution. This assumes the cited URLs themselves are truthful and credible.
But the judge doesn't check the source's credibility.
No, that's beyond the scope here. It assumes the source is valid once accessed. It also assumes critical info can usually be tied to individual pages, which might not always be true for really fragmented information.
What about using LLMs in the judge itself?
Good point. Reliance on LLM-based judgments. While their extractor and verifier were incredibly robust, 99% correct, LLMs can occasionally make errors.
But they mitigated that.
Yes, with rigorous human validation. And remember, that validation even found human errors, reaffirming the judge agent's reliability for these specific tasks. It's a complex mix of human and AI intelligence in the evaluation itself.
Any other limitations?
Finally, limited analysis on black box systems.
We can't see inside.
Right. It limits the ability to fully interpret why one performed better than another at an architectural level, or estimate precise costs like token usage. They report time and answer length, but the inner workings are opaque, which can slow down broader research.
Okay. Now, really big picture. Broader impacts and ethical considerations.
Profound, really. The promises are transformative. Agentic search could fundamentally change how we interact with the web.
Reducing cognitive load, boosting efficiency.
Yes. Democratizing sophisticated search for everyone, supporting better decision-making in fields from education to healthcare. The potential for human augmentation, offloading that mental grunt work, is immense.
But there are risks.
Significant potential risks. The paper acknowledges them. Misinformation is a big one. Advanced systems could generate seemingly credible but totally false or unsupported information, maybe even convincing narratives.
Weaponized hallucination.
Could be. Then there's malicious use. Bad actors exploiting these systems for large-scale disinformation, or maybe unauthorized data extraction, at scales we haven't seen before.
And bias.
Yes, perpetuating existing biases from the web content they learn from. This could lead to discriminatory outcomes if not very carefully monitored and mitigated. We need guardrails.
How does Mind2Web 2 help with these risks?
Well, its role is crucial. By emphasizing rigorous evaluation-structured rubrics, explicit source attribution verification, the benchmark directly helps develop more transparent and accountable systems.
Standardizing evaluation helps build safer AI.
Exactly. It accelerates trustworthy system development and promotes clarity about capabilities across research and industry.
Is there a downside to this kind of benchmark?
There's a nuanced ethical concern, the risk of overfitting to benchmarks.
Teaching to the test.
Sort of. If rubric-based evaluation becomes widespread, it could lead to automated mass production of training data, maybe via reinforcement learning, especially by big players.
Which might improve scores on the benchmark.
Right, but it risks overfitting. Agents get great at the benchmark tasks, but might amplify biases in the rubrics themselves, and then perform poorly or weirdly in the messy, unstructured real world. Optimizing for the test, losing general ability.
How do they counter that?
Cleverly. They maintain a private test set, and they keep the judge agent scripts and the generation pipeline hidden.
So you can't directly train on the evaluation mechanism.
Exactly. It encourages agents to develop true information-seeking skills, not just memorize the benchmark.
What about websites changing? Does that break the benchmark?
They acknowledge that.
Yeah.
But the design focusing on broad goals, not specific click sequences, makes it less sensitive. And they commit to long-term maintenance, reviewing tasks, getting feedback, ensuring integrity.
Okay. So wrapping up, what does this all mean for, us, for the learner, the information seeker in this crazy digital world? Agentic search clearly represents this profound paradigm shift, moving from us doing the assembly to intelligent, autonomous AI research. And Mind2Web 2 gives us this crucial, rigorous platform to evaluate and push these complex systems forward.
It's a huge step.
And while AI still faces big hurdles, that pervasive hallucination, really mastering dynamic, time-varying info,
Significant challenges remain.
it is rapidly closing the gap on human performance in those tedious, detail-heavy tasks. Sometimes, like you said, even outperforming us.
The progress is undeniable.
This raises an important question for all of us, doesn't it?
What's that?
As AI takes on more and more of our legwork in gathering complex information, freeing up our mental energy from the repetitive stuff, what new human capacities will this freedom allow us to develop? And maybe more importantly, what new forms of oversight, critical thinking, and discernment will be absolutely vital for us to master in a world increasingly augmented by these tireless AI agents?
That's the big question, isn't it? How do we adapt and evolve alongside this technology? What skills become paramount?
A lot to consider as we navigate this evolving digital landscape where how we find and use information is changing so fast. Until next time, keep diving deep.